In this video, we will discuss the basic mechanism for an SN1 reaction. Now, the best way to learn about SN1 is to compare it with SN2. So let's begin by reviewing what I hope you already know about the SN2 reaction. For example, do you know how many steps are there in an SN2 reaction? Remember that after each question that I ask, I hope that you'll pause the video and come up with your answer. I hope you answered that there is one step in an SN2 reaction. Next question, what happens in an SN2 reaction during that one step? I hope you answered. Here's the answer we discussed in the previous video. In that single step, two things happen simultaneously. The nucleophile joins the alpha carbon, and the leaving group leaves the alpha carbon. Now, we all are familiar with the terms nucleophile and leaving group. How can we define the term alpha carbon? In the SN2 series, we defined an alpha carbon as the carbon connected to the leaving group. And later in this video, we'll have to expand that definition so that it's more useful for an SN1 reaction. I hope that that was all easy review for you. Now we need to move on and learn the basics about an SN1 mechanism. So first question, how many steps are there in an SN1 reaction? Well, did you know that there are two steps? There are two steps in an SN1 reaction. That's really the most basic and most important fact to know about an SN1 reaction, that it's two steps. So you can see that the names of these reactions are a little unfortunate or a little misleading. The term SN2 has the number 2 in its name, which might make you think that it has two steps, but it doesn't. It only has one step. And the term SN1 has the number 1 in its name, and that might make you think that it's a one-step reaction, but it isn't. It's a two-step reaction. At the end of the previous SN2 series, I explained why the number 2 is in this term SN2 reaction, and maybe later in this series we can explain why the number 1 is in the term SN1 reaction. But for now, you should know an SN1 reaction has two steps. Well, the next natural question is for me to ask you, how would you describe precisely what happens in those two steps? I hope you actually paused the video and tried to describe exactly what happens in those two steps. Well, the answer is that what happens in those two steps is exactly the same as what happens during an SN2 reaction, except that these two things happen simultaneously in an SN2 reaction, and these two things happen in separate steps in an SN1 reaction. In the first step, the leaving group leaves the alpha carbon. Then, separately, in a second separate step, the nucleophile joins the alpha carbon. I hope that you'll carefully compare this description with this description for SN2 so you can see how they're similar and how they're different. Do you see that the things that happen in an SN1 are exactly the same as the things that happen in an SN2? Leaving group leaving the alpha carbon and nucleophile joining the alpha carbon. So how are they different? They're different because in an SN2, these two things happen simultaneously in the same step, whereas in an SN1, first the leaving group leaves the alpha carbon, and then separately, in a separate step, the nucleophile joins the alpha carbon. So make sure you understand the similarities and differences between the mechanism for SN2 and SN1. This material on the screen is crucial fundamental material for your Ochem success. Now would be a good time to pause the video and make sure you have all this information thoroughly memorized. Now we need to start applying these basic ideas to some actual problems. Let's apply these ideas to some actual SN1 mechanisms so we can see what these steps look like in practice. Please pause the video and try this problem. Now let's discuss the problem together. Well, here's a checklist of actions to carry out for each reaction. We already talked about many of these steps in the SN2 series, but this also has some new steps that will help us with SN1 reactions. We should start by numbering all the carbons in the starting materials. like so. Now, these numbers are for our own personal use. They're not intended for official IUPAC naming, so you can number the carbons in any way that you like. You can number the carbons in the starting material in any way that you like. Now, we need to look for ionic bonds so we can identify formal charges. We should know that sodium is a metal and bromine is a nonmetal, so there will be an ionic bond between the sodium and the bromine. Sodium is a metal from the far left of the periodic table that's willing to give up electrons and end up with a positive formal charge. Bromine is a nonmetal from the right of the periodic table. That means it wants electrons. It'll pull the electrons towards itself and give itself a negative formal charge. We talked in detail about how to use ionic bonds to assign formal charges in the SN2 series. Now we can start trying to assign roles. And you want to start by assigning roles to the atoms with formal charges. Well, a Br minus, we know that an atom with a minus charge is likely to play the role of nucleophile. So we expect that because of its negative charge, the bromine will act as a nucleophile. The negative charge makes the bromine want to donate electrons. Now, what about this positive sodium? You might think that the sodium is reactive because of its positive formal charge, but we learned otherwise in the SN2 series. In the SN2 series, we learned that atoms with formal charges are likely to participate in the reaction, like the Br-, but we learned that metals with positive charges are an exception. A metal like sodium with a positive formal charge is usually a spectator, which does not participate in the reaction. So we expect that this sodium will be an unreactive spectator ion. We can identify this neutral chlorine atom as our leaving group. What is the clue that the neutral chlorine will be the leaving group? Simply that we've memorized that neutral chlorine is a good leaving group. Notice that the neutral halogen is the leaving group and the negative halogen is the nucleophile. That shows how crucial it is to focus on the formal charges. To review, we've identified Br- as our nucleophile, neutral chlorine as our leaving group, and sodium plus as our unreactive spectator. And notice that all of those identifications are consistent with the rules that we learned in the previous video. In the previous video, we learned that a negative formal charge can indicate a nucleophile, such as on Br-. In the previous video, we learned that a neutral chlorine is a good leaving group. And in the previous video, we learned that a metal with a positive formal charge, such as sodium plus, is an unreactive spectator. Now, since we've identified this chlorine as the leaving group, we'll identify carbon-2 as our alpha carbon, because remember, we're defining the term alpha carbon to mean the carbon connected to the leaving group. Now we have to determine the mechanism. How do we determine, is this reaction going to be SN2, SN1, E2, E1? How can we tell? Well, in the previous SN2 series, we learned that for most courses, the best way to tell is to use a table. We'll look at a table to determine the mechanism. Here is a handout that contains that table that I was discussing. You'll find a link to this handout in the video description box. It's important to have this table printed out. So if you don't already have the table printed out, now would be a good time to click the link in the video description box and please print out the handout so that you can have this table in front of you. Notice that this handout also summarizes the key information about SN2 and SN1 that we were reviewing earlier. There is one step in an SN2 reaction, during which the nucleophile joins the alpha carbon and simultaneously the leaving group leaves the alpha carbon. There are two steps in an SN1 reaction. Two steps in an SN1 reaction. In the first step, the leaving group leaves the alpha carbon, and in the second step, the nucleophile joins the alpha carbon. Now, actually, what I said here is that there are two main steps. I refer to these as the main steps because there may also be an acid-base step in an SN1 reaction. We'll learn about those acid-base steps later in the series. So the best way to put it is that these are the two main steps in an SN1 reaction. Let's use the table. To determine the row of the table, we have to decide whether our alpha carbon is primary, secondary, or tertiary. Well, this alpha carbon is tertiary. Always write down what type of alpha carbon you have. So we're in this row of the table for a tertiary alpha carbon. Do you remember the definition of tertiary carbon? A tertiary carbon is a carbon that's attached to 3 carbon chains. Notice we don't count the bonds. Obviously, carbon-2 has 4 bonds. For that matter, carbon-1 has 4 bonds. If you count the hidden hydrogens, all the carbons here have 4 bonds, but we're not counting the bonds. A tertiary carbon is defined as a carbon attached to 3 carbon chains. Well, carbon-2 is attached to 3 carbon chains, so it's tertiary. And to figure out which column we're using, we identify our nucleophile, Br-. Here's Br-, it's in the middle column of our table. So if we're in the middle column and the bottom row, the table predicts that the major mechanism will be SN1. Always write down the name of the mechanism. This is very important. Always write down the name of the mechanism. Of course, the table also predicts that E1 would be a minor mechanism here, but the question was asking for the major mechanism. So for this problem, we'll just focus on the SN1 and disregard the E1. How do you figure out what type of mechanism you're going to be using for this type of problem? Well, the best approach for most classes is to use this table. Notice that we followed our checklist. We used the table to determine that the reaction was SN1, and then we wrote down the name of the mechanism. Make sure you write down the name of the mechanism. Now the next step is to draw electron pushing arrows. Now, how do we draw those? Well, we have to remember this is an SN1 reaction. There will be 2 steps. Do you remember what happens in the first step for an SN1 reaction? Well, we've memorized that in the first step of an SN1 reaction, the leaving group leaves the alpha carbon. So we need to show the electron pushing arrows for that to occur. Well, in the previous video, we reviewed how to draw the electron pushing arrows for a leaving group. The electron pushing arrow for a leaving group looks like this. Notice it should not look, say, like this. That would be wrong. Remember that the head of the arrow goes on the atom, because remember, a leaving group is supposed to receive electrons to leave an atom. So the electron should be moving towards the chlorine so it can receive electrons while it's leaving carbon number 2. And that's the only electron pushing arrow we'll draw for this first step. There's only one thing happening in this step, so there's only one electron pushing arrow for that step. So we did this. We drew the electron pushing arrow for this step. Now we're ready for the next step, which is to draw the products of this first step. Notice that you should not start drawing the products until you've finished drawing the electron pushing arrows. Now that we have the electron pushing arrow, now we can draw the product from that step. Here are some rules for how to draw the products of a mechanism step based on the electron pushing arrow. I've already numbered all the carbons in the starting material. Now, each arrow tells you to erase a bond, draw a bond, or both. Do you think that this arrow tells us to erase a bond, draw a bond, or both? I hope it's intuitive that this arrow tells us to erase a bond. Erase which bond? This arrow tells us to erase the bond between carbon-2 and the chlorine, because the tail of the arrow is on the bond between carbon-2 and the chlorine. So here I've shown products where I've erased the bond between carbon-2 and the chlorine. Notice that I'm continuing to number all the carbons in the products that I'm drawing, and I'm writing down numbers that are consistent with the numbers that I wrote down over here. Now, that I think is the easy part. Here's where people mess up. The most important part of this picture to get right is the charges. How do we get the charges right? Well, for every mechanism step, we should change 2 charges. We should change a charge at the beginning of our string of arrows and a charge at the end of our string of arrows. Who is the atom that's losing electrons at the beginning of our string of arrows? Notice that in this case, there is only one arrow. The string or series of arrows is just this one single arrow. Who is losing electrons from this arrow? Well, I hope it's clear carbon-2 is losing the electrons from this arrow. the electrons are starting in this bond and they're moving into a lone pair on the chlorine. So carbon 2 is losing the electrons in this bond. So what should be the new charge on carbon 2? Carbon 2 started neutral and it lost electrons. Electrons have a negative charge, so carbon 2 should become one step less negative. That means one step more positive. That means carbon 2 should end up with a positive formal charge. That's the most important part of these products to get correct. And we also changed the charge on the chlorine. The chlorine started neutral and is gaining electrons, so the chlorine should end up with a negative formal charge. This is really crucial. We always change two charges for every mechanism step. The most common mistake that students make is forgetting to change the formal charge at the beginning of the arrow. The most common mistake students make is forgetting to change this charge on carbon 2 at the beginning of the arrow. But what is the most important part of these products to get right? The charges. So if you left out this positive charge, that's terrible. You have to get the charges correct. That's the most important part of the products. I hope you'll carefully study these rules for changing two charges. You need to memorize that for every mechanism step, you need to change two charges. If there's only one arrow, you change the charge at the beginning and the end of the arrow. By the way, you can see that I'm going through the steps for this problem extremely slowly to make them as clear as possible. Obviously, eventually you'll have to learn how to go through the steps of a mechanism much more quickly than this, but it's appropriate for this first example to proceed very slowly to explain everything as clearly as possible. Now we have to decide, are we done or do we need another mechanism step? Well, it should be obvious that we're not done. We need another mechanism step. There's two ways to see that the mechanism is not finished. First of all, our main product here has a formal charge. Well, that's a strong clue that we're not done with the reaction. Remember, we saw in the first video, nature doesn't like charges. So usually the reaction isn't finished until we've gotten rid of the formal charge on the main product. So we don't think we're done because we haven't gotten rid of this positive formal charge on the main product. That's this rule. And of course, we can be confident that we're not finished here because we know we're doing an SN1 reaction, and we've memorized that an SN1 reaction has two steps. So since we've only done one step so far, we can be confident that we need to do a second step. Going back to our checklist, we drew the products for the first mechanism step, and then we asked whether we had finished the mechanism. We decided we hadn't finished the mechanism, so we have to redo some of the previous steps. For example, we should go back and redo this step. Now we have to identify what roles atoms will play in these starting materials for the second step. So you need to remind yourself what's going to happen in step 2. Do you remember what happens in the second step of an SN1 reaction? Step 2, the nucleophile needs to join the alpha carbon. Now, we already know we're going to use the Br- as our nucleophile, and we've identified carbon 2 as the alpha carbon. Now notice that carbon 2 is no longer attached to the leaving group. So we need a more expanded definition of alpha carbon if we're going to keep calling carbon 2 the alpha carbon. Previously, we defined the alpha carbon as the carbon attached to the leaving group. Well, that definition doesn't help us here where the leaving group's not attached anymore. So let's expand this and say that a carbon with a positive formal charge will also be called an alpha carbon. That way the carbon that's called the alpha carbon in this picture can still be called the alpha carbon in this picture. This is the definition of alpha carbon that's useful for the material we're covering now. Later in the course, you'll learn other useful definitions for the term alpha carbon. So we'll continue to call carbon 2 the alpha carbon based on this definition, that it's the carbon with the positive formal charge. So remember, in this step, the nucleophile should join the alpha carbon. We need to draw the electron pushing arrows for that new mechanism step. Well, in the previous video, we reviewed how to draw the electron pushing arrows between a nucleophile and an electrophile. Oh, actually, I guess I should go on then. I have to identify which atom will be the electrophile. So we're going to identify this alpha carbon as the electrophile because we know the nucleophile is going to join that alpha carbon. So carbon 2 here will be our electrophile. Now remember, whenever we identify a role, we want to identify the clue that the atom is playing that role. What's the clue that carbon 2 will be the electrophile? Well, the clue is that this is a carbon with a positive formal charge. In the previous video, we learned that when there's a positive formal charge on a carbon, C+, that's a strong clue that the carbon will act as an electrophile. The positive formal charge makes the carbon want to receive electrons as an electrophile. By the way, I'll mention that when a carbon has a positive formal charge, a carbon with a positive formal charge also has an incomplete octet. And that incomplete octet is a second reason, so to speak, why we would expect that carbon to want to receive electrons as an electrophile. Now you can see why it was so crucial to include this positive formal charge in this picture. Remember, the most common mistake students make is forgetting this positive formal charge. But if you forget this positive formal charge, there's no particular reason to think that carbon 2 will be the electrophile. Based on this picture, you might think that it might be carbon 1 or 4 or 3 or none of them that could be an electrophile. It's only when we put in the positive formal charge that we have the tool that we need for figuring out which of these carbons will be the electrophile. That's a good illustration of why the most important part of the picture to get right is the formal charge, because you use the formal charge to figure out what will happen in the next step of the mechanism. By the way, don't bother trying to assign delta charges now. When we assign a formal charge to a molecule, we usually do not assign delta charges. Formal charges are more important than delta charges. So since we've assigned a formal charge here, we're not going to assign any delta charges here. By the way, also notice that I did not label carbon 2 as the electrophile for the first step, because actually this carbon did not play the role of electrophile. It wasn't until after the leaving group had left that the carbon is now going to play the role of electrophile. So I'm not labeling it as the electrophile until this step. But wait, what about the sodium plus? What role do we expect this positive sodium to play in the reaction? Well, again, in the previous video, we saw that when we see a metal with a positive formal charge, such as sodium plus, that's usually an unreactive spectator ion. So we don't expect this sodium plus to play any significant role in the reaction. Now we can draw our electron pushing arrows, now that we've labeled the roles, and we know that the arrows should go from the nucleophile, which is the electron donor, towards the electrophile, which is the electron receiver. We've seen that electrons should move away from the nucleophile towards the electrophile. So here's the correct electron pushing arrow to show the nucleophile joining the alpha carbon. Now that we've drawn the electron pushing arrow, we can draw the products for this step. Remember, don't start the products until you've finished the electron pushing arrow. Well, every arrow tells you to erase a bond, draw a bond, or both. Can you guess or figure out what this arrow would tell you? I hope it's intuitive that this is an arrow that tells us to draw a bond. Between which two atoms? It should be obvious that we're going to draw a bond here between the bromine and carbon 2, because the arrow goes from the bromine to carbon 2. Remember to keep numbering all of your carbons consistently with the previous picture. Here I've drawn the new bond between the bromine and carbon 2. Now the most important part to get right is to change two charges. Remember that you change a charge at the beginning and end of the arrow. So I think it should be pretty clear here that the bromine is the beginning of the arrow. The bromine started negative and it's losing electrons, so the bromine should change to neutral. I've actually already drawn it as neutral. And it should be clear that carbon 2 is at the end of this arrow, so we're going to change the charge on carbon 2. Carbon 2 started positive and it's gaining electrons, so carbon 2 should get back to neutral. And in fact, I've already changed the charge on carbon 2. Back to neutral. Now, should the Na plus still be ionically bonded to the bromine? Well, no, because the bromine has lost its negative charge. Remember, an ionic bond is based on an attraction between a positive and a negative charge. The sodium and the bromine are ionically bonded here because their positive and negative charges attract each other. But in this picture, the bromine has lost its negative charge, so now there's no longer any reason for the positive sodium to be attracted to the bromine. So we will no longer show an ionic bond between the sodium and the bromine. So how should we draw the sodium in the products? Well, in the previous video series, we saw that the best approach is just to leave out the sodium completely. Since the sodium is just being an unreactive spectator ion, it's really not of any interest to us. So most professors would be satisfied if you just leave the sodium out completely from the products. So for most courses, the best way to handle a spectator ion is simply not to draw it at all in the products. So we won't draw the sodium at all in these products for simplicity. So now we're ready to ask again whether we have finished the mechanism or we require another mechanism step. Well, there's a strong clue now that we're done with the mechanism. And the clue is that our main product has no formal charges. When the main product has no formal charge, that's a strong clue that you're done with the mechanism. That's a rule that's especially useful in the first semester of organic chemistry. Now, do you see why I'm saying the main product? Oftentimes you can't get rid of all the formal charges. For example, we still have a formal charge in this product. There's still going to be a formal charge on the Cl-, and for that matter, there's a formal charge on the Na+. There's no way to get rid of those formal charges, but I hope it's clear that this is what we would consider the main product of the reaction. We were able to get rid of the formal charges on this main product of the reaction, and that's a strong clue that we've finished the mechanism. There are some exceptions to that rule. For example, towards the end of the SN2 series, we saw that SN2 reactions are actually an exception to this. We saw in the previous series that the main product of an SN2 reaction can end with a formal charge, but that's a little bit unusual. Usually when we're doing an SN1 reaction, we're not going to say that the reaction is finished until the main product has no formal charge. Now, another clue that we're finished is that we've finished our second step. We've learned that an SN1 reaction has 2 steps, so it's not surprising that we're finished after the second step. But you shouldn't rely that much. You shouldn't rely that much on that clue, because remember, really, an SN1 reaction has 2 main steps, but sometimes you might also need an acid-base step. So although there are 2 main steps for an SN1 reaction, there also might be a third acid-base step sometimes. We'll learn about that later in this series. But in this case, we can see we don't need an acid-base step. How do we know we don't need an acid-base step? Because we've managed to get a main product with no formal charges, even without an acid-base step. So that can make us confident that we've finished the mechanism. And you can see why I would say that the most important part of the products to get right is the formal charges. If you don't draw the correct formal charges, you can't tell whether you're done with the mechanism or not. The way we know we're done with this mechanism is that there's no formal charges left in the main product. Looks like we finished the problem. I'll put a box around this to show that this is our major product. Well, the main purpose of this example was to help us learn the basics of the SN1 mechanism. So I hope you can see now more clearly what it means that an SN1 mechanism has 2 steps. And you can see more clearly what happens in those steps. In the first step, the leaving group leaves the alpha carbon. And here's the way to draw the electron pushing arrow for that. Then in the second step, the nucleophile joins the alpha carbon. And here's the way to draw the electron pushing arrow for that. We learned that we can refer to the alpha carbon as the carbon that's attached to the leaving group, or in this picture, the carbon with the positive formal charge. That helps us to interpret these steps. And we saw how to use this checklist. We've numbered all the carbons in all the starting materials and products, trying to number all the pictures consistently. We drew formal charges for this ionic bond. In each step, we labeled which atoms would play which roles. In the first step, the chlorine was the leaving group, and in the second step, the bromine was the nucleophile, and carbon-2 was the electrophile. Always try to identify the clues that tell you which atoms will play which roles. For example, the clue that carbon-2 would be the electrophile in this step is that it's a carbon with a positive formal charge. label the alpha carbon and write down whether the alpha carbon is primary, secondary, or tertiary. You have to do that because we use that to determine the mechanism. The fact that this was a tertiary alpha carbon helped us to determine that the mechanism was SN1. We saw how to use the table. We saw how to use this table to figure out the mechanism. Always write down the name of the mechanism. Draw the electron pushing arrows for the mechanism step. After you draw the electron pushing arrows, draw the products for that step, numbering the carbons consistently. And how do you know when you're done? You're usually done when the main product has no formal charge. As long as the main product still has a formal charge, you're probably not done with the mechanism. It took us a long time to discuss all of these steps because we were going slowly for clarity, but with practice, obviously, you can learn to move through these steps much more quickly. Nevertheless, I would definitely recommend at this point that you should write down what I've been writing down. Write down the names of the roles that I've been writing down. Certainly write down all the formal charges. Write down whether the alpha carbon is primary, secondary, or tertiary. Write down numbers for all the carbons. Write down the name of the mechanism. So, as a beginning Ochem student, you should be writing down, when you do these problems, everything that I have in this large circle. Everything that I've written down in this large circle is stuff that would be useful for you to be writing down on each of these problems. Writing these things down will help you to make fewer mistakes and to build your organic chemistry knowledge and comfort level. In particular, I really encourage you to write down at this point always the roles that each atom is playing in the reaction steps. And definitely to write down the numbers for the carbons and all the other details that I have in this big circle. Let's get some more practice with this important SN1 mechanism. Please pause the video and try this problem. I hope you really did try this problem on paper. Now we can discuss. It would be good to start by numbering all of the carbons. After that, we can look for ionic bonds. We see an ionic bond between the metal sodium and the non-metal iodide. And we can put in the formal charges like so. We can start identifying roles. Because of the negative formal charge, we can expect this iodide to play the role of nucleophile. The neutral bromine could play a role of leaving group, because we've memorized that neutral bromine is a good leaving group. Our alpha carbon is the carbon attached to the leaving group, so carbon 2 is the alpha carbon. Well, that's enough detail that we can now choose our mechanism. Now, how do you choose the mechanism? I hope you chose the mechanism by using the table. I hope that you didn't just assume that this reaction would be SN1. Don't make that assumption, because when you take your exam, you can't assume that the reaction is SN1. You have to figure out the mechanism on each exam problem. So I hope that you're actually going to be using this table for each of the problems in this video series, not just assuming that they're SN1. All right, well, to figure out the row, we have to decide that this is a tertiary alpha carbon. Make sure that you write that down. It's a tertiary alpha carbon because carbon 2 is attached to 3 carbon chains. That puts us in the bottom row of our table. Our nucleophile is I-, which puts us here in the middle column. Middle column and bottom row predicts that the major mechanism is SN1. E1 will be the minor mechanism, but the problem was asking for the major, so we'll just focus on SN1. Make sure you actually write down the name of the mechanism. One of the most common mistakes students make is saying that the reaction is SN1, but then accidentally drawing the mechanism for SN2. So make sure you actually write down the name of the mechanism. Now we need to draw our electron pushing arrows for our first step. And in order to do that, we need to remember what happens in the first step of an SN1. Well, you should have memorized that in the first step of an SN1, the leaving group leaves the alpha carbon. It should be easy to draw the electron pushing for arrow like that. Here's the electron pushing arrow that shows that the leaving group is receiving electrons as it leaves. After you draw the electron pushing arrow, only then can we draw the product of that step. This arrow tells us to break the bond between carbon 2 and the bromine. Break the bond between the bromine and carbon 2. Now, the most important part of this picture to get right is the formal charges, and we know we need to change 2 formal charges at the beginning and end of this arrow. Carbon-2 is losing electrons at the beginning of the arrow because carbon-2 is losing the electrons from this bond. Carbon-2 started neutral and it lost negative electrons, so carbon-2 becomes positive. The bromine gained electrons. Bromine started neutral and gained electrons, so the bromine becomes negative. Remember, the most common mistake that students make is forgetting to change the charge at the beginning of the arrow, forgetting to put in this positive charge on carbon-2. Make sure you put this positive charge in when you drew the mechanism. Are we done? Well, we can see that we're not done because our main product still has a formal charge. And of course, we expected another step anyway because we expect at least 2 steps for an SN1 reaction. So now we should identify the roles for this next step. Well, first of all, we have to know what's going to happen in this next step. What happens in the second step of an SN1 reaction? What happens is that the nucleophile should join the alpha carbon. We should keep labeling carbon-2 as the alpha carbon. Now we refer to this as the alpha carbon because it's the carbon with the positive formal charge. We'll expect this iodide with the negative charge to be the nucleophile. Now we have learned that when we see a positive charge on a carbon, that carbon is electrophilic. Carbon-2 will be the electrophile because it's a carbon with a positive formal charge. What role do we expect the positive sodium to play? Well, we've learned that positive sodium, a positive metal, is an unreactive spectator. We can draw the electron-pushing arrows. Notice that first you should identify the roles that are being played and then draw the arrows. That's the way to make fewer mistakes and to build your organic chemistry skills as a beginning student. First, write down the roles, then write down the arrows. We know that electron-pushing arrows should go from the nucleophile towards the electrophile. That's the only arrow we need here to show the nucleophile joining the alpha carbon. Now, after we've drawn the arrow, now we draw the product from that step. This arrow tells us to draw a bond between the iodide and carbon-2. Make sure you change 2 charges. The iodide started negative and it lost electrons, so the iodide changes from negative to neutral. Carbon-2 started positive and it gained electrons, so we change the charge on carbon-2 from positive to neutral. Are we done? Well, we would think that we are done because our main product now has no formal charge. There's no way to get rid of the formal charges on the Br- or the Na+, but our main product here has no formal charge, and that's an indication that we're done with the mechanism. Well, the main purpose of this was to give us more practice with SN1. There are 2 steps in an SN1. In the first step, the leaving group leaves the alpha carbon, and in the second step, the nucleophile joins the alpha carbon. Here's how you draw the electron-pushing arrows for those steps. Recall that the name of this mechanism is SN1. Now, where does this name come from? Do you know what does the S stand for in SN1? Answer: the S stands for substitution. SN1 is called a substitution reaction because we are substituting one thing for another thing. In this case, we're substituting the nucleophile at the position where the leaving group used to be. For example, in this example of an SN1, we substituted a iodide in the position that the bromine used to occupy. So when you replace one thing with another thing at a certain position in a molecule, that type of replacement is called a substitution reaction. Do you know why the term SN1 has the letter N in its name? What does the N stand for? Answer: the N stands for nucleophilic. The thing that is getting replaced in this molecule is the bromine, and the thing that is replacing it is a nucleophile. So this is called a nucleophilic substitution because it's a nucleophile that's going to take the place of the previous thing that was in this position in the molecule. In the term SN1, S stands for substitution, N stands for nucleophilic. Why does this term have the number 1 in its name? Well, it's certainly not because there's one step. We know that actually SN1 has 2 main steps. So this does not stand for the number of steps. I'm actually not going to explain what the number 1 stands for in this term right now. Hopefully I'll get a chance to explain the significance of the number 1 in this term later in this video series. Remember, what is the most important tool for drawing the correct electron pushing arrows? The most important tool for drawing the correct electron pushing arrows is the formal charges. Well, here's the rule that we reviewed in the first video in this series. Let's make sure that each of our arrows are consistent with this. Take a look at this first arrow. I would say this first arrow is going, at the beginning of this arrow we have carbon 2, and at the end we have the bromine, and those are both neutral. So that's consistent. It's okay to have a neutral atom at the beginning of the arrow and a neutral atom at the end of the arrow. So here's a neutral atom at the beginning of the arrow and a neutral atom at the end of the arrow. So that's consistent. And this arrow turned out not to use any of the formal charges. And then looking at this arrow, notice that the arrow starts on a negative formal charge. Well, that's a good sign. It's a good sign when an arrow starts on a negative formal charge. And this arrow ends on a positive formal charge. That's a good sign. It's a good sign when an arrow starts on it's a good sign when an arrow ends on a positive formal charge. So this arrow definitely is consistent with our formal charges. It would certainly be a big mistake if the arrow was pointing like this. That would certainly be wrong. You would never want the electrons to move from a positive towards a negative. Instead, it makes sense for the electrons to move from the negative towards the positive. Notice that we usually like to use formal charges with our electron pushing arrows, but actually in this first step we drew an arrow that did not involve any formal charges. It simply had a neutral atom at the beginning and end of the arrow. Well, that's also consistent with our rules. Always pause to make sure that the electron pushing arrows that you're writing down are consistent with the formal charges. In these mechanism steps, there was only one arrow. There was only one arrow in this step and only one arrow in this step. So this is how you judge a mechanism step based on the formal charges if there's only one electron pushing arrow for that step. Here again is the checklist of things to try to do for each reaction. Notice how we completed each of these steps. We numbered all the carbons in the starting material. We drew formal charges for this ionic bond. We labeled the roles that atoms would be playing, both in the first step and then again in the second step, leaving group, nucleophile, and electrophile. We labeled the alpha carbons. That's important for SN1 and SN2 reactions. We wrote down that this was a tertiary alpha carbon. That helped us in the next step where we used the table to determine the type of mechanism. We wrote down the name of the mechanism. If you don't write down that the mechanism is SN1, it's easy to get confused and accidentally start doing the mechanism for an SN2 reaction. Let me emphasize that. In the previous video series, we got lots and lots of practice with SN2 mechanisms. And now we're trying to shift gears and start doing SN1 mechanisms. Well, if you've already gotten a lot of practice with SN2 mechanisms, it's very easy to accidentally do an SN2 mechanism even when you know that the mechanism should be SN1. So try to avoid that mistake. Try to be very conscious of doing the correct mechanism. And one way to be conscious of that is to actually always write down the name of the mechanism you're doing so that you don't forget what the right mechanism is in the middle of the problem. For example, I oftentimes see students do this. I oftentimes see students say, aha, this is an SN1 mechanism, but then they still draw the mechanism as if it were SN2. They show the nucleophile attacking at the same time as the leaving group leaves, so try to avoid that mistake. I think that's a tempting mistake to make because it might feel weird for the leaving group to leave when nothing is pushing it off. Sometimes this feels weird to students. Students feel, why is the leaving group leaving, even though nothing is pushing the leaving group off? Well, you just have to have memorized that if the mechanism is SN1, then that really is what happens. In the first step, the leaving group leaves the alpha carbon without anything pushing off the leaving group. Maybe in a later video in this series, we can explain why it can make sense for the leaving group to leave, even when there's nothing pushing it off the alpha carbon. But for the time being, you just need to have memorized that even if it might seem a little bit weird, that's what happens in the first step of an SN1. The leaving group leaves the alpha carbon without anything pushing the leaving group off the alpha carbon, so to speak. That's SN1. So make sure you write down the name of the mechanism. Remember, don't begin drawing the products for each step until you've finished drawing the electron pushing arrow for the step. Also notice how we kept numbering the carbons, and make sure that your numbers are consistent. So for example, here would have been some bad numbers. Oftentimes I'll see students do something like this, and maybe some students might call these carbons 7, 8, 9, 10, and 11. Well, that's useless because those numbers are not consistent with these numbers. The purpose of the numbers is to tell you which carbons are the same in different pictures. So I want to give this carbon the same number as this carbon to show that they're the same carbon even though they are in different pictures. So number your products consistently with your starting materials. I give this carbon the number 1 to show it's the same carbon as this carbon 1. I give this carbon the number 2 to show that it's the same as this carbon 2. So make sure that your numbers are consistent with the numbers you used in the starting materials. Why? Why should you number all these carbons? Because if you don't, you could easily accidentally add or drop a carbon. If you don't put in numbers, if you don't number the products, it would be easy to make a mistake and accidentally add a carbon. This product is wrong because I accidentally added a carbon, but that might be hard to tell without the numbers. If you don't add the numbers, it might be easy to make a mistake and accidentally drop a carbon. This is wrong because it's dropped a carbon, but it would be easier to see that if I was numbering all the carbons. Number all the carbons, because that will help you to avoid accidentally adding or dropping carbons. And we decided when we were finished with our mechanism by checking whether the main product had a formal charge. This did not seem like the final step because this product still had a positive formal charge. This seemed like the final product because now the main product had no formal charge. I hope when you tried this problem on your own, you actually tried to complete these steps in the checklist. So you should have written down everything I have in the big circle here, numbering all the carbons, writing down the roles, labeling the alpha carbon, writing down the name of the mechanism, writing down the formal charges. At this point, try to model your scratch work on the scratch work that I'm modeling for you in the videos. That's the way to make progress in Ochem, by building good habits as a beginning Ochem student. Let me ask you a question. How many steps are there in an SN1 reaction? I hope you answered 2 steps. Let me ask you another question. What happens in those 2 steps? I hope you paused the video and answered that from memory. Well, here's the answer. In step 1, the leaving group leaves the alpha carbon. In step 2, the nucleophile joins the alpha carbon. You need to have that memorized. And I hope you also have memorized what happens in an SN2 reaction. Those key ideas about SN1 and SN2 are here on the handout and here on the handout. So now that we've learned these basic ideas about SN1, does that mean we're done? Are we now masters of the SN1 reaction? Well, unfortunately, it's more complicated than that. It's more complicated than that because remember I mentioned that there's 2 main steps in an SN1 reaction, but there may also be an acid-base step. And in fact, there usually is an acid-base step for an SN1. Most SN1 reactions involve an acid-base step. Most SN1 reactions involve an acid-base step. So we're not done yet. Now we need to learn how to add an acid-base step to the overall SN1 mechanism. Now, in order to do that, first of all, we just need to review what acids are and what bases are and how to draw the mechanism for an acid-base step. The SN1 mechanism is oftentimes one of the very first mechanisms that you learn in your Ochem class. So at this point, you might not be that strong on how to draw the mechanism for an acid-base step. So in the next video in this series, we're going to do a general review of how to identify acids and bases and how to draw the electron pushing arrows for an acid-base step. And then we can apply that to the SN1 mechanism.